looking at the different classes, and we started with the first class, which is the nitrogen mustard. That's the name that is given to them, nitrogen mustard. But within, of course, that class of nitrogen mustard, it's just one category of the alkylating agents. We have, of course, the different other quite a number of compounds which are actually nitrogen mustards, but their mode of action is alkylation. So, of course, the simplest is where what we call chlomethine or meclomethamine, and meclomethamide is when R is a methyl group. So indeed, so I see what you're talking about, the general structure. So indeed, this is the general structure of the nitrogen mustards, and what changes is this R. And you can see for meclomethamine or chlomethine, R is a methyl group. Then you have melphalan, also nitrogen mustard. Again, what changes is our R, and it is phenylalanine. So we can even call it phenylalanine mustard, because the phenylalanine starts from there. That's all of that group is phenylalanine and represents the R. Then you have again the uracil mustard. You can see this uracil, of course, which is a pyrimidine, uracil mustard. So again, this is the R which changes. Then you have estramustine. Estramustine, even look at it. Let me put the pointer, sorry. Again, when we look at estramustine, we are talking about the same thing, and the whole of this, all that, going this way, which is a steroidonuclease, is our R. And then, of course, from there we go to chlorabusel, and if you look at this group here, it's a phenyl butanoic acid. Again, that's our R. And then we have, of course, a slight difference in the structure, but basically the same. But I remember we had discussed this, where you have ifosfamide. And if you look at ifosfamide, we had noted that the chloroethyl groups are on different nitrogen atoms, and that I had said is the difference between ifosfamide and cyclophosphamide. But you can still see we are still having the kind of the same. So that, of course, there are two of them, and we can say this is the whole of that is our R. So again, we have ifosfamide and then beta-mustine. And when you look at beta-mustine, this is a benzimidazoline. This is a benzimidazoline there. And we have beta-mustine. Again, this is our R, and this is our group. So when we look at all these drugs, there's something that is coming out very common in all of them. Of course, they have the R, and they must have the two ethyl chloro groups are also important for activity. But you can see the difference is in the R, and when you make that R different, you will change their pharmacokinetics, you change their distribution, you change their toxicity, as we are going to see in a minute. So the R is very, very important. Alkylating agents, nitrogen mustards, they are dialkylating agents, because you can see they have two groups. They have two ethyl, the chloroethyl groups are two. One mustard molecule can alkylate two nucleophiles, because as we are going to see, it has two centers of electrophiles, it has two electrophiles, and therefore it can either do interstrand alkylation, or you can do intrastrand alkylation. In inter is where you have those two DNA strands, two of them joined together, two different strands being joined together. In intra is where within the same strand, you can pick one guanine and join it with another guanine. And therefore, of course, still have an interference with the replication. And the mode of action is what we are looking at now. And the first step is where you have an acid-base reaction to release their own pair of electrons on the nitrogen. So that's the first step, that there is an acid-base reaction. This is because most of these drugs, as you see them here, they are usually given as their acid formulations. So you might find that this is protonated with an inorganic acid to give us meclomethamine hydrochloride, melphalan hydrochloride. So if you add a base, then of course you are going to release. You add a base, you are going to release the base. You add a base in terms of a base or an acid, but this time you add a base. It will release for you the nitrogen, so that the nitrogen will not be protonated. Because if you have an acidic salt, you add a base, then it will mean the acid will be neutralized, and you'll be left with your salt. You'll be left with your base not in the form of a salt. So acid-base reaction to release a lone pair of electrons on the nitrogen. Then the lone pair of electrons on the nitrogen displaces the chloride to give the highly reactive aziridinium cation. In other words, what we are saying is that these drugs are like prodrugs. They must be activated. And once they are activated, they must generate what we are calling an aziridinium cation. We're going to look at that in a minute. And that aziridinium cation is an electrophile, highly reactive, very, very highly reactive. It can attack either proteins, it can attack also the DNA, and of course, once it attacks the DNA, then it will bring about alkylation. And this process can be repeated provided a second living group is present. And you have seen in most of the nitrogen mustards, you have two active groups, and therefore you can't repeat that process. So here we have our, let's say, like meclomethamine hydrochloride. And all I'm saying, we are saying is if you add base, because this hydrochloride is hydrochloric acid, you will neutralize the hydrochloric acid, and now you will release your lone pair of electrons, which are on the nitrogen, because here the lone pair of electrons has already reacted with hydrogen, so that nitrogen is positive. So if that's the first reaction. When that happens, and that of course can happen in the body at the pH 7.4. So you release the lone pair of electrons, and once you release the lone pair of electrons, then now you have the formation of the aziridinium ion. Remember this chloro group. Chloro groups are electron withdrawing groups. And because they're electron withdrawing groups, they can easily leave. And they usually make this carbon here. Remember, this is a carbon. This carbon has much lower electronegativity compared to the chlorine. So the chlorine, this bond, it has pulled the electrons towards itself. So this carbon is usually positive. And therefore, that positive carbon can therefore be attacked. Remember, the attack is always from the nucleophile or from the area of electron density. So this nucleophile can therefore attack that carbon there. And in so doing, of course, that chlorine, already which is already negative, will easily leave. And once that happens, this is what we are now calling the aziridinium ion. So all that has happened is this carbon here coming and attacking that nitrogen, attacking that carbon there and giving us the aziridinium ion. If you look at the nitrogen, it will have four bonds, and therefore it will be carrying a positive charge. Now this is a highly reactive positive ion, highly reactive electrophile, and it can either attack tissues, proteins, or it can attack the DNA. And once it attacks the DNA, then you will have, this is a nucleophile. Whatever nucleophile you have, whether it's a DNA nucleophile, centers of the, and remember, we say like if you're talking about guanine, position number 7 of guanine is a good nucleophile. Position number 2 of guanine is a good nucleophile, and also position number 3. Position number 6, I think the oxygen, we did mention also the oxygen of cytosine is also a good nucleophile. So those centers which are good nucleophiles then can be attacked by this aziridinium ion. And once they are attacked by that aziridinium ion, then, so when they're attacked by that aziridinium ion, then the nucleophile, the attack is different. When the nucleophile, let me put it correctly, when the nucleophile attacks, because it's a center of electron density that attacks, when the center of electron density within the nucleophile attacks the aziridinium ion, it opens and the nucleophile is, or the DNA is alkylated. This is the alkyl group. That's why we are talking about alkylation, because this is a 2-carbon atom, and it is an alkyl group, alkylated. Then you can still see your lone pair of electrons is still available. So we can still repeat the process. Again, this nucleophile attacking this, loss of that, having our aziridinium ion going back. But this time, of course, this one now will be this. So it will already be alkylated. So now this now forming an aziridinium ion, and it can alkylate. And then you can have alkylation of another nucleophile. So such that now the the nitrogen mustard, is joined or has alkylated 2 nucleophilic sites. It has alkylated 2 nucleophilic sites, and that's what we are saying. It could alkylate the 2 nucleophilic sites on the same strand or on different strands. If it alkylates 2 nucleophile sites on different sites on different strands, that is what we call cross-linking. So it can cause cross-linking where this strand is linked to the other strand, and for sure if that happens, no separation can happen. It will stop replication immediately. It can also alkylate two nucleophilic sites within the same strand, again cause disruption even in the type of bonding that you have, and hence again disrupt replication. And structure activity relationship. So we are saying that is our general structure. So our interest is to understand this group here. How can that group be changed? Like when we look at a meclomethamine, that is a methyl group. What do we know from other studies that we have done about alkyl groups? We know alkyl groups are electron donors. Alkyl groups are electron donors. And because they're electron donors, that means they donate electrons into the system. And once they donate electrons into the system, that means they will make this nitrogen more nucleophilic. They are giving it more electrons, make it more nucleophilic, and therefore accelerate the formation of the aziridinium ion, accelerate the rate of attack, and hence they are highly reactive. That can be dangerous in that if that drug is very highly reactive and you give it orally, it might never get to the site of action, because it's very highly reactive. It will form the aziridinium ion even within the GIT before it gets the site of action, and that is usually can result in a lot of toxicity. So the structure of the nitrogen master differs only in the nature of the third group, R attached to the amino nitrogen. This group can either be aliphatic or it can be aromatic, and is the prime determinant of the chemical reactivity, how fast it will react, oral bioavailability, and the nature and extent of side effects, as I have said. Aliphatic groups like methyl push electrons to the nitrogen, thus increasing the rate of formation and reactivity of the aziridinium ion. Because if you increase the electron density here, this becomes a very strong nucleophile, and therefore it will attack this carbon even much faster, and therefore increasing the rate of reactivity, and unfortunately also increasing the toxicity. So meclomethamine you find very, very active. It can react with water, it can react with blood, it can react with tissues. It is too reactive to survive the oral route and has to be administered intravenously. Very, very reactive, and of course having a lot of toxicity, because remember, when a drug is not selective for the receptor, you want it to be selective for the specific tumor, it does not even have the time to get there, therefore resulting in a lot of toxicity. Then you can have other drugs, like if you look at melphalan, chlorabusel, we see now R is different. R is an aromatic group. And again, we've done a lot about aromatic groups. Aromatic groups withdraw electrons through resonance. They withdraw electrons through resonance. And of course, nitrogen will donate electrons through resonance. It will withdraw electrons through negative inductive effect, but the resonance predominates. Therefore, it means the lone pair of electrons, which is found here on this nitrogen here, will move in here. That you have a double bond here. Once you have a double bond there, definitely one of this bond must move. So it can move such that this carbon here, there, carries a negative charge. And there is no double bond. The double bond disappears, that carbon carries a negative charge. That means that some of the electron power of the nitrogen has moved to the aromatic ring, which means you have reduced the electron, the nucleophilicity. You have reduced the nucleophilicity of the nitrogen. What does that mean? You will reduce reactivity. You will reduce toxicity. That molecule can be given already. That molecule can also get the site of action. So that's what is very important for us to understand, that group, as we have said, it will determine the oral bioavailability, the reactivity, and so on, as we have mentioned. So we are seeing aromatic nitrogen, and we have melphalan, we have chlorabusel. They stabilize the end lone pair of electrons through resonance. Resonance delocalization significantly slows the rate of intramolecular nucleophilic attack, azridinium ion formation, and DNA alkylation. So ultimately, it reduces the rate of alkylation. So the ultimate reactivity of the drug is reduced because, as we have said, the nitrogen lone pair of electrons will participate in the delocalized system of the aromatic ring, therefore decreasing the aromaticity of the nitrogen. The higher stability also provides aromatic mustards have a reactivity sufficiently controlled to permit oral administration and attenuate the sensitivity of side effects, and we can't be able to explain. The higher stability also provides a chance for enhanced tissue selectivity by giving the intact mustard time to reach the malignant cells before generating the electrophilic azridinium ion. So we are therefore saying, when you do an aromatic substitution, you reduce toxicity, you change, you can be able to give the drug orally, and also you increase on the selectivity, as I've explained. Alkylating agents, the nitrogen mustards. So what are our SARs? Very simple. Mainly, we are changing the R group. But we can say, first and foremost, the ethylene moiety between nitrogen and the chloro group is essential for activity to form the azridinium. So we must have the ethylene moiety. The ethylene moiety is this group here. This is our ethylene moiety there. So that moiety or that alkyl group is necessary to allow us to form the azridinium ion. If you change that ethylene group, you change it into a CH2, or you change it into 1, 2, 3, or into a 3-carbon atom, you can abolish activity. Halogens other than chloro group also decrease the activity. So those are some of the things that we are saying that you require the ethylene group, and if you want, of course, we are going to see sometimes the longer the alkyl group, it can help us, especially when we are talking about intrastrand alkylation. But what is most important is to note that you do require an alkyl group between those two the nitrogen and the chloro group for maximum activity. And aliphatic group, they push, as we have seen, they push electrons to the nitrogen, and we have seen methylamine more reactive, too toxic for oral use. Direct injection into the tumor is even preferable. They will bring about extravasation. Is common. Extravasation is when the drug leaks, and because of the fact that this drug is highly reactive, it destroys the blood vessels. So there can be a lot of extravasation. Antidote is sodium thiosulfate. We will see how you can treat when you give meclomethamine, especially via injection, and there is leakage and there is extravasation, then you can be able to give sodium thiosulfate to be able to trap the azridinium ion, which is being formed within the tissues and bringing a lot of the inflammation and extravasation. And then aromatic R group, here already said, like in mefran or like in corabusel, they stabilize the nitrogen by resonance, reduce rate of azridinium ion formation, less reactive, less toxic, can be administered orally. There is where we have, that's our clomethine or clomethamine. We have already looked at all those drugs, so we do not need to go there. I think the one I was thinking about changing the chain was a different group. So therefore, we are saying all those SARs hold that the ethylene moiety is very important for formation. You require an ethylene moiety, you change it to a methyl group or a propyl group, you abolish activity. Halogen other than chloro group will decrease the activity. So those are the known SARs of these compounds. Then we are saying, if you give this drug, especially we have said you have to give it IV, and you're trying to give it directly into the directly into the tumor. Of course, when you inject, as we have said, you can cause a lot of intravasation. Then you can apply, or you can give. You can again give sodium thiosulfate, and the sodium thiosulfate, all it will do is that it will trap. To be able to trap either the azridinium ion or even deactivate the drug itself. So if you look at that, is our again, meclomethamine, it's the one which causes a lot of extravasation, and that is sodium thiosulfate. So this is sodium thiosulfate. The thiosulfate ion is S2O3. So you can see that there. So all it is doing is that it will combine. It will replace the chloro group there, and also that replaced by the chloro group, and the resultant molecule that is formed is highly stable, very highly stable. Again, even if you have formed the aziridinium ion within the tissues, again the thiosulfate will help it to do the same thing, and it will give us that molecule, which of course will give us stability, but will also give us stability. The resultant compound is stable, and therefore this is just helping in case some of the drug has leaked. You are injecting, some of the drug has leaked into the tissues. You can apply the sodium thiosulfate, because you see the tumor is not within the tissue. You want the drug to go to the actual tumor, but unfortunately it has leaked and it's causing necrosis of the tissues and extravasation or inflammation of the veins. Therefore, you give this drug, and it will deactivate any of the drug that has been left at the site of action. So yes, the site of administration, any of the drug that has been left at the site of administration. Now, when we are looking at these compounds, we mentioned, so yeah, we have that, we also included ifosfamide, and I think I left out another one, which is cyclophosphamide, but the structure of cyclophosphamide is very close to ifosfamide. Both again, ifosfamide and cyclophosphamide require to be activated. If you look at this is a cyclophosphamide, as I had said earlier. In cyclophosphamide, the nitrogen is attached to the phosphorus atom, and then of course the two chloroethylene moieties are coming from the nitrogen. So this drug, as it is the way it is, as it is now, it is not active. It must be activated in the body through metabolism. So it is metabolized by the mixed function oxidases or the cytochrome P450 enzymes, and what happens is that there is hydroxylation. You get hydroxylation 1, 2, 3, 4. You get 4 hydroxylation, and once you get the 4 hydroxylation, this molecule is highly unstable. So therefore, it tautomerizes, or it can cleave, not even tautomerize, very highly unstable. It cleaves, and that is in equilibrium. It cleaves to give us that compound here, and you can see that cleavage is just happening here. It cleaves at this point, at that point there. But normally, even before it cleaves, this hydroxyl group can first be oxidized to the ketone. And then readily cleaves. Oxidized to the ketone, and then it readily cleaves. And then that, once it cleaves to give us this compound, but also the hydroxy cyclophosphamide can also be deactivated or metabolized by alcohol dehydrogenase. You know, alcohol dehydrogenase, we have the alcohol dehydrogenase will oxidize the hydroxyl group to that compound. So indeed, if you get this going into this compound, then that molecule is inactive. Also, this compound, which is in equilibrium, this is the aldehyde, is in equilibrium with the alcohol aldehyde, and in equilibrium with the alcohol. Again, it can be acted on this time by aldehyde, because this is an aldehyde, so the enzyme we call it aldehyde dehydrogenase. This is an alcohol, the enzyme we call it alcohol dehydrogenase. So it can be acted on by aldehyde dehydrogenase, and if that happens, all we are doing is this aldehyde there, you are oxidizing it to the carboxylic group. There is nothing else that is happening to that molecule. Everything else remains the same, and that is also that is a metabolic pathway for cyclophosphamide. Now, so that's a metabolic pathway. Even this other is a form of metabolic pathway, but the metabolic pathway that is used for activation. It is indeed being metabolized, but at the same time, that metabolism is required for activation. So now, once you have the aldehyde formed, that is the aldehyde formed, then you can have shifting of electrons, of flowing of electrons. These electrons can come and move in there. If that moves in there, this will be now a double bond. will form a double bond. So this carbon will have 1, 2, 3, 4. So therefore this bond breaks. That bond breaks and the electrons come here. So this oxygen acquires a negative. I hope that is clear. I repeat again. All that is happening is the electrons of this double bond, an electron from this bond comes in here and you get a double bond there. Once you get a double bond there, it will mean that you get a double bond there. Remember this carbon here, although we have not indicated, it has 2 hydrogens. It's a CH2. It has 1, 2, 3. There is another extra hydrogen. So if you put a double bond there, that carbon will have 5 bonds. That is not possible. So you cleave that bond there. Once you cleave that bond there, the electrons. So of course we have said this has become a double bond. Sorry, let me repeat it again. So this here is moving here to this here. And since this one has gone away, this carbon is still satisfied with 4 bonds. The one which is suffering is this one, as I said earlier. This is a carbon which will have a problem because it will have, it already had 2 other, it had a CH, a hydrogen. Remember, whenever this is line notation, so it does not show, but there is a hydrogen and another hydrogen. So already this has already 4 bonds. So if this comes in here as a double bond, this carbon will have 5 bonds. It's not possible. Then therefore the cleavage will happen there. So once the cleavage happens there, then one of the electrons will come here to give us an oxygen minus. So the 2 electrons will go back, but remember one of the electrons is from the carbon atom, so it will come here and this oxygen will carry a negative charge and there will be a cleavage there. So this compound left here will be oxygen, double bond, carbon. Carbon, double bond, carbon. So oxygen, you can see oxygen here, oxygen, double bond, carbon. Carbon, double bond, carbon. And that is the compound we are calling achlorine. Achlorine. So by again, this is this of course a spontaneous rearrangement, here. It's a spontaneous rearrangement or spontaneous cleavage which is occurring here. It is not being catalyzed by any enzyme. It is a spontaneous cleavage. You get the compound we are calling achlorine. Here there is an N. Achlorine. Now achlorine is highly toxic. It causes renal are not part of the cyclic ring. Lost in my connection, guys. Hope it's back. So the only difference is that you have opened up the ring. So therefore, phosphoramide it's no longer cyclo. Remember, it was cyclophosphamide. Now it's phosphoramide. You've opened up the ring. So now you make this is now the active moiety. This is the active moiety, and this is the toxic moiety. Achlorine is the toxic moiety. The phosphoramide, of course, is the active moiety, and of course also causes toxicity. So from there again, the same thing. This has lone pair of electrons. It attacks that slightly electrophilic carbon, gives us the aziridinium ion. This is the one which is left there. Gives us the aziridinium ion, and the aziridinium ion will be attacked by a DNA or a protein, but most probably a DNA, and of course that DNA will be alkylated. Then the process can repeat again. Then you repeat again. This will have the lone pair of electrons. Again, it will attack here, and it will form the aziridinium ion on this, and therefore there can be double alkylation, as we have said. So this is a process the cyclophosphamide has to undergo, one, for its metabolism, and also for its activation for the purpose of activity. So cyclophosphamide must be activated if indeed it's going to have any activity. next one is, now we have said, of course, we are saying this drug, the Alkylating, is highly toxic. So we need to know also how do we reduce the renal toxicity. So this is the same thing. It's just this is ifosfamide, sorry. So the first one we did was cyclophosphamide. Ifosfamide also requires to undergo also activation, just the same, and you find that the ifosfamide is given as the RS racemic mixture. It is given as the RS racemic mixture, and again, the first thing that can undergo, it can undergo a metabolism through cytochrome P450 or mixed function oxidases, either to remove this group there or to remove that group there. That's why we are saying if you can remove this group there through oxidation, or you can remove this group here through oxidation. And since it's given as the RS racemic mixture, that's why we are saying it can give you this. So if you look at this, is ClCH2CHO. So ClCH2, ClCH2, CH double bond O. So it's you can see this is an NH. So there is oxidative dealkylation there, and this is left. So this will be left as an amino group, and this is leaving as chloroacetaldehyde. I'm only saying you can have oxidative dealkylation or oxidation there, catalyzed by cytochrome P450 enzyme, and you can cleave that. If you cleave this one, it will give you, so you can get two products. You can either get the 2 or the 3, considering this is position 1 there, that is position 2. If you cleave that one, then you will get the RS2 dichloroethyl you get the 2 dichloroethyl isophosphamide. So if you cleave off that, we are only considering that this will be to position 2. If you cleave these, then it will be position 1, 2, 3. You will get the 3 dichloroethyl isophosphamide. Or ifosfamide, not iso, but ifosfamide. So if you cleave it here, it's position 1, position 2, position 3. It will be RS is to show that it is the racemic mixture. It's dichloro because you've removed the dichloro, you've removed the chloro. The group which you've removed is chloroethyl. So it's dichloroethyl ifosfamide. So it's either 2 or 3, depending on which one is cleaved. And either of them is cleaved through oxidative dealkylation. So that process can happen. And once that process happens, then the resultant molecule is indeed inactive. The resultant molecule is inactive because it will not be lacking to not have these groups, so it cannot have any anti-cancer activity. Or the alternative route is having ring hydroxylation, again via or through mixed function oxidases or cytochrome P oxidases, and again you have 1, 2, 3, 4, so you get 4-hydroxy ifosfamide. I hope you can see that. Saying that position 1, 2, 3, 4. So ring hydroxylation, again catalyzed by cytochrome P450 enzymes, and you get the 4-hydroxy phosphomide, and that now can this hydroxyl group can be oxidized, or in fact it's an interchange. Remember ketoino tautomerism, so it can undergo kind of ketoino tautomerism, and it can exist either as the alcohol or it can exist as, this is not true ketoino, it's ketoino tautomerism. It can exist as the alcohol or it can exist as the ifosfamide, which is a ketone. So ketoino tautomerism there, and the resultant compound can also undergo, when you get a ketone. So remember, ketone there means you have that. You have a double bond here. Oxygen. So that compound, out of ifosfamide, can also undergo further oxidation. If it undergoes further oxidation and this compound and this group here becomes a carboxylic acid, it will cleave there. So all that will happen is that you will open up this compound, that will be on its own and that will be on its own. And that's what we are calling the carboxy ifosfamide. So the aldehyde ifosfamide can be further oxidized by aldehyde dehydrogenase to give us the carboxylic derivative, which is a ifosfamide, again, which is not active. Now, where we get activity is where now the aldo ifosfamide now can cleave. The aldo ifosfamide can cleave to give us achlorine, just like cyclophosphamide and also the ifosfamide mustard. So you can see it has done the same thing as the cyclophosphamide because it has just opened up. It has just opened up. It's only that, of course, the effect of the exultant compound is almost the same. So it has opened up, and in opening up, it has given us the ifosfamide mustard, and now this is the one which is responsible for activity. That again, just as we looked at the cyclophosphamide, that will be responsible for toxicity. One is responsible. This. In fact, the only difference is that this hydroxyl group in the phosphoramide mustard is an amino group. So this is the one which now is responsible for activity, and it will do the same thing we have done. We have said this portion here. This is a lone pair of electron. This portion here forms the aziridinium ion attacked by the nucleophile. After that, this forms again the aziridinium ions again attacked by the nucleophile. So all we are saying is that all we want is to open up the cyclic ring, to open up the ring so that we have an open chain metabolite. You have an open chain metabolite, and the open chain metabolite is the activated form of the ifosfamide, which indeed will easily form the aziridinium ion, and the aziridinium ion will alkylate. Aziridinium ion will very readily alkylate the DNA. So this is just a very simple way, what we have just looked at, the ifosfamide through oxidative dealkylation to give us either the 2 or 3, the same thing, chloroacetamide. All this is this process we want. This lower one is the one which is giving us the phosphomide mustard, and that this is the one which is indeed the active moiety. Now, we have said one danger of these drugs is their toxicity, renal toxicity. So how do we sort out the renal toxicity? And the renal toxicity of this compound is sorted out by giving a compound we call mesna. Mesna is 2-mecaptoethane sulfonic acid. Mesna is 2-mecaptoethane sulfuric acid. So it has an ethane moiety on one side. It has a sulfonic acid, and then it has an SH group. And all it does is that, again, it is able to deactivate the achlorine. It is able to deactivate the achlorine, and therefore, I think I have it somewhere, I'm hoping. It's able to deactivate the achlorine, and therefore reduce the toxicity. So toxicity of cyclophosphamide can be treated with mesna, which has SH group or sulfhydro groups. So again, you can see, and it's not only cyclophosphamide, even ifosfamide, both cyclophosphamide and ifosfamide, but cyclophosphamide causes more toxicity than ifosfamide. So all that we're saying, we go through the process we had said of activation. So remember, we go through this, giving us the hydroxyl group, and then the cleaving, and once it cleaves, and then once it cleaves, it gives us the phosphoramide. Once you get the phosphoramide gives you the active moiety, and this active moiety is what you're saying you can mop it up. So remember, we are saying mesna will have a hydrogen here, it will have a hydrogen there. It has a sulfate group there, a sulfonate group there, and it has an SH group there. So, but in the body it exists as a free ion. So it exists having a negative ion there and a negative ion there. Therefore, all that happens is that in place, so it can replace this chloro group, as you can see. So all that has happened, CH2, so you have the SH binds on the sulfhydro portion, and the S CH2CH2SO3. That terminates the activity of that compound. Or also, you can also have the mesna actually acting with the cyclophosphamide when after hydroxylation, after it has undergone hydroxylation, just before it has been completely activated to give us the phosphoramide compound, then you can also have it reacting with the mesna. In other words, in case there is too much of it, then you can be able to minimize the toxicity. And of course, also of most importance is that the mesna also can react with acrorine. Remember, we said when you get the phosphoramide, you also get acrorine, and acrorine, as I have said, has renal toxicity. So the acrorine can also be reacted with mesna, and this is what is most important. And if you administer mesna when you are giving cyclophosphamide, it will be able to remove the acrorine as the drug is being excreted, or as the drug is being removed from the body, and therefore minimize the renal toxicity. So therefore, the toxicity of cyclophosphamide is actually prevented by administration of mesna. So we are saying this is what I was just going back for us to see that. So mesna is 2-mercaptol ethane sulfonic acid. You have the CH2CH2SO3 on the other side, and it's a subhydro compound that is used to reduce the incidence of hemorrhagic cystitis associated with certain chemotherapeutic agents. We have ifosfamide and also cyclophosphamide as example. It is converted to a free thiol compound in the kidney. So within the kidney, it is converted to a free thiol compound in the kidney. It binds to and inactivates acrorine and other urotoxic metabolites of ifosfamide and cyclophosphamide. It reduces the toxic effects on urinary tract during urinary excretion. So that's the advantage of mesna, and it has that sulfhydro group that can be able to attack that sulfhydro group that can be able to actually act. It is acting as a nucleophile and replacing the chloro group, and help for deactivating both the cyclophosphamide and even the toxic metabolite, which we are calling acrorine. So that is of importance, that cyclophosphamide, ifosfamide must be activated in a slightly different way from the others. Also, the others were being activated, but those ones are not really prodrugs. Those are not prodrugs because they are only forming the active ion in the process of their mode of action. But these other ones, they are inactive when given, and they must be activated through metabolism. They must be activated through metabolism, and therefore they qualify to be prodrugs. The next class, so that is the first class of the alkylating agent. The next class of alkylating agents is the nitrosoureas, and they include camustin, romustine, and streptozotocin. Streptozotocin, we also looked at it under the antibiotics, but it is indeed, it's an antibiotic, naturally occurring, but its mode of action is that it's an alkylating agent. It is, and its structure, it is a nitrosourea, and its mode of action is actually an alkylating agent. Again, when you look at these drugs, you can see you have then this is what we are calling the nitroso. That's why we are calling them, that's nitroso. And if you look at them also, this is a group we are calling the urea. All of them must have that group, nitrosourea. Nitrosourea there, and of course also nitrosourea. So all of them will have that common group, which is nitrosourea. They can differ in their structures. If you look at them, they do have two groups. So you have the nitrosourea, or that the whole of this portion there. So that portion, which is found in all of them, and then you can say that portion therefore can have an R on that side, and it can have an R on that side. So the nitrosourea can be substituted with two different groups, which can be the same, Can be the same group, they can be same groups, or they can be different. But all these compounds do contain what you are calling the nitrosourea, and that is why they qualify to be nitrosoureas. If you look at the first one, which we are calling the lomustine, you can see it has, of course, the nitrosourea, and one of the R groups is a cyclohexane moiety, whereas the other one is the chloroethyl group. So this other one is the chloroethyl group, and of course, this is a group that is causing this drug to do alkylation. So that is the group there. We are going to look at the mode of action. The mode of action or the activation, again, these compounds must be activated. When you look at camustin, it has two of the ethyl chloro groups. Chloroethyl groups are two, and because of the second addition, then camustin becomes more active than lomustine. If you look at streptozotocin, you find that one of the R's is that group there. It's a methyl group, and the other R is here, which is a glucose moiety. So one of the R's is a glucose moiety, and the other R is a methyl group. So all of them do satisfy what we have said. And when you put the two chloroethyl groups, then you find camustin has very high lipid solubility, it penetrates the blood-brain barrier, and it can be used for brain tumors. Let us look at their chemistry, and of course also we are saying they also have to generate. They must, as they are not active, they must generate the active component. Remember, the active component must be an electrophile. So when they get into the body, they are able to generate the active component, and on generating the active component, then that active component is the one that is the one that alkylates the DNA. These compounds are reasonably stable at pH 4.5, but they will undergo both acidic and base. They will undergo both acidic and base catalyzed decomposition at either lower or higher pH, respectively. So they can be stable at pH 4.5. That is basically quite a bit acidic. So if the pH is higher than that, and you know the pH of the body is 7.4, they will undergo decomposition. The decomposition leading to alkylation, the decomposition then forms the ion, or forms the moiety that leads to alkylation of the DNA. And that process, the first move is that you have hydrogen extracted from these drugs. If you look at these drugs, all of them on the side of the urea nitrogen, there's no hydrogen on this side. But if you look at them, you see that they do have all of them. One of the nitrogen has a hydrogen substituent, and therefore what happens is that you have extraction or removal of that hydrogen. So these drugs at that point, if you look at this nitrogen, because of that nitrogen, remember the nitrogen is highly electronegative. So this nitrogen is withdrawing electrons from this hydrogen, and therefore this compound is actually behaving like an acid because it is donating a proton. So there is extraction of a hydrogen from that to leave a negative charge behind. So that's what we are saying. So all of them have abstraction of the NH proton, which is relatively acidic, followed by rearrangement to give an isocyanate and a diazo hydroxide. We're going to see what happens. I think first of all we look at it when we read that. So in the summary is here, you have the nitrosoureas, there is decomposition, they decompose. When they decompose, they give us the isocyanate and the diazo hydroxide. The isocyanate can be able to carbamylate proteins and even RNA. The diazo hydroxide is the one which undergoes further decomposition to give us the final carbocation. Which actually, carbocation is where you have a carbon which carries a positive charge. And that carbocation is the one which is thought to do the alkylation. So that is in a very simple way. So now when we look at it in details, so we are saying that, see, we are putting that as an R. That is our R there, and that is our hydrogen. So there is extraction. So in other words, we are saying since this hydrogen is acidic in nature, this compound loses that hydrogen and is behaving as a weak acid. And on losing that proton, then you will find that this will carry a negative charge. When that carries a negative charge, then that negative charge moves inside there. And when that moves inside, this will be oxygen, double bond carbon, double bond nitrogen R. So this carbon cannot carry any other bond. So this bond breaks there and the electrons move there. So now this becomes a double bond there. I hope we are together. There is a double bond, there is a cleavage there. So now on this side we'll have the chloro group, CH2, nitrogen, double bond, nitrogen, double bond, oxygen. So that's what we are calling the diazo hydroxide. This is our diazo. Yeah, is there. That's our azo group there, and you have your hydroxide group there. And then you have, this is your isocyanate ion, and we have said it is formed just from here, that electron there, this electron moving in, and you have a double bond there. And there must be a cleavage there. This generates the isocyanate, and that generates the diazo hydroxide. So the diazo hydroxide, so we have said there's isocyanate, it can do carbamylation. It's a carbamoyl group. It's a carbamate, so it can do carbamylation of either proteins or RNA. But what is really thought to react with the DNA is the further decomposition of the diazo hydroxide. So the diazo hydroxide again adds or accepts a proton. So it accepts a proton acceptors are bases, so it's behaving here as a base, accepting a proton to give us the hydronium ion here. So this oxygen here is now having positive charge. So give us a hydronium ion, and then this is a very unstable compound, and this bond automatically cleaves, and once it cleaves, the electron goes to this hydronium ion to generate water, and of course you have. So that will go there, but for this to go there, that is started by the lone pair of electrons of the nitrogen. So the lone pair of electrons from the nitrogen moves in here, so you have a triple bond there. This nitrogen cannot survive. So that triple bond there, and there will be a cleavage at that point, and that bond there satisfies the oxygen, which is deficient of electrons, so that this will give you water, and now this will continue to give you that molecule there. And once you get that molecule there, then that molecule loses a nitrogen, and you can see you have formed what you can call a chlorocarbon-cation. The cation here, you can see the CH2 is the one which has a charge, because this nitrogen left with, so that nitrogen left with, that when that nitrogen left and that bond is broken, then you find that that carbon is deficient of one electron, because that leaves as a nitrogen, it's deficient of one electron, and therefore it will carry a positive charge. And again, that carbocation is the one which is responsible for alkylating the DNA. So you find now that is our carbocation here. Yeah, that is our DNA, which has been alkylated. And of course, then this again now is also able to alkylate, of course, not through the same mechanism, but remember the chloro group can leave, giving us another cation there, which can again alkylate another DNA. And therefore, you can have DNA nucleophile, so you can see this CH2 at the middle, CH2, and that chloro group leaves and another DNA molecule enters. So again, we are saying the activation of course, the nitrosoureas is very different from the activation of the cyclophosphamide. We can't say it is starting with the nitrosourea behaving as an acid, and of course losing a proton, and of course when that happens, the resultant molecule is unstable. There is spontaneous movement of electrons followed by decomposition to give us the active moiety, of course the precursor of the active moiety, which is a diazo hydroxide, which further accepts a proton, and the process goes on. And what we want to generate is the reactive carbocation. That reactive carbocation, because it's a very powerful, it's a very potent electrophile, very potent. Remember, the chlorine is pulling electrons, very potent electrophile. Then it can acrylate the DNA. So that is the same thing that we have looked at. So it's, the only bit is the end here where we have it as alkylated. This is the carbocation alkylated. Let's say we have guanine. Let's say you have guanine and it has an alkylated position 7 and it's sticking out. Then again, this one can be lost and this comes and joins there, perhaps to another guanine. And you can see now this is interstrand alkylation, or what we call cross-linking. There is no way this DNA can be able to, there is no way it can be able to divide. No way at all can it be able to divide, and therefore these drugs can cause, of course, they will stop replication, and it will result in cell death. The other drug we mentioned, so that was these were the first ones where you have where they struck the mustin and the lomustine and carbamustine, which have of some structural similarity. But when you looked at streptozotocin has a slight difference in its structure. So it has just a slightly different way of activation, but not very different. So again, this is reacts with water. So as you can see, it reacts with water, and once it reacts with water, the water causes hydrolysis. So this group here, there is hydrolysis at that particular portion. So there is hydrolysis, and once there is hydrolysis at that portion, you can see the group you'll be left with. This is a CH3 group here, remember, CH3, N, it leaves us with CH3 there, N, and so there's this CH3 group, which is this one, and then there's a nitrogen, double bond, nitrogen, OH. So that is the group that, when on hydrolysis here, that is a group that is formed. And this group again is not stable, again is able to form our carbocation. It's able to form now again our carbocation. So it's able to form this ion here with the CH3 and triple bond there. So the lone pair of electrons, it's like that lone pair of electrons here comes in there. But it must be doing the same thing we had said: acquire a proton, have a hydrogen, and then the lone pair, I think, to do what we had said first, whereby most probably to this you could acquire hydrogen, and then the lone pair of electrons comes in. The lone pair of electron here comes in to stabilize that, and that electron comes there. Just that bit is quite similar to give us this ion, and this ion again can break down to give us the methyl group. The way we say it, this, remember the short form here. So this will lose then the N2, and it will result in CH3 positive. So just the way we said last time, that it loses that this group, there is a cleavage. So you have a cleavage here. So, or the one of the electrons comes this way, as we had said earlier, had explained, to stabilize that positive nitrogen, and now this leaves as a deficient carbocation as a CH3 positive. So the other one, because remember the others had CH2Cl, so they left as a carbocation, which was CH2 positive, CH2 positive, CH2Cl. So that's a bit different, because this one is it's a methyl group. Remember this drug has a methyl group here. And because you see the others on this card are CH2Cl, so the alkylating group was a CH2 positive, CH2Cl. But now here it's a methyl group. So once it cleaves completely, it will give you a methylene carbocation, and that is what is going to alkylate your DNA. So that's streptozotocin, which we said, of course, it is an antibiotic naturally occurring, but at the same time, it is a nitrosourea that is, of course, from its structure. It is a nitrosourea, and of course, its mode of action is where, of course, first of all, it is generating the carbocation, and it is that carbocation that the carbocation is the one which does the alkylation. So it is an N-methyl N-nitroso derivative of 2-deoxy glucose. We are calling it 2-deoxy because you can see this position, that's position 1, position 2, that position will be having a hydroxyl group, but that position is substituted or with another group, and that's why we are calling it 2-deoxy glucose that possesses cytotoxic and anti-cancer properties. It composes in aqueous solution with the release of dinitrogen via methyl diazoic acid. This is what we're calling methyl diazoic acid. It uses the dinitrogen, and once it uses the dinitrogen, it will also release a methyl group. So it will give you the dinitrogen, the N2 plus a methyl cation. And of course, that cation is the one which causes the methylation. So it causes methylation. It can cause methylation at N7 and carbon 6 of guanine, or it can cause methylation at N1, N3, N7 of adenine. So it can, we had already said some of the positions which are highly nucleophilic, and that will be readily alkylated. So it's important to note that these compounds must form the aziridinium ion, but they are not forming those ions through metabolic process. And that's why we are not calling them prodrugs, but the others are forming through metabolic processes. So structural activity, relationship,